Hello students, um, in this particular lecture we will be dealing with a combination of bars which are located in a particular plane. All of the bars are in a fixed plane, but they are located with respect to some inclinations with respect to each other. That means all the bars are not parallel to each other, they are at some inclinations. Obviously, this sort of a structure finds applications in plenty of structural examples where they are supposed to load, where they are supposed to sustain a external loading. So the technique is going to be explained with the help of an example which we are going to solve. And since um, the structure which we are taking corresponds to plenty of bars arranged together with the help of pin joints, each of the bar can basically be treated as a as a case in which we have derived the equation previously. Each of the bar is going to be treated similar to what we have derived as a stiffness matrix previously. So the example is we are going to take a combination of three bars which have been connected together with pin joints. So this happens to be the global frame, that is the positive x and the y axis, and these are the three bars. uh, all the ends of the bar are constrained, they are constrained with respect to the pin joints, and these are the three elements. Each of the bar is going to be taken as an independent element, and this corresponds to the global node numbering. You can very well see that each of the bar has been taken as an independent element. Each element has two nodes uh, at the two ends, and there happens to be a global reference frame also. Now the style of analysis which we are going to follow, basically it has its inspiration from the structural approach which basically is being carried out by the civil department, but still the approach is going to be important from the FEM point of view, as it is going to illustrate the concept of breaking the problems in simple manageable parts and combining them together for analysis. We already know the force and the displacement relationship for a bar element, and this is given by the equation on display. Uh, since each of the bar is going to be broken down into a linear element having two nodes, one at each end, therefore we have two displacements which obviously are the unknown, and two forces acting at the nodes. Also note that this particular relationship which is on display is applicable only in a particular coordinate frame in which the x-axis is oriented along the length of the bar element itself. This relationship uh, is applicable only for a coordinate frame in which the x-axis is oriented towards the length of the bar element itself, and in fact is not going to be applicable for any other coordinate frame. The stiffness matrix obviously is of size 2 by 2 because there happen to be two unknown, and what we want is a similar relationship existing between the various degrees of freedom and the forces acting on the nodes, but this relationship is required to be found in a global coordinate system. So in the figure There happens to be a bar element which has a length L. Obviously, there are two coordinate frames in the picture. One that is indicated by dashes. Uh, in this coordinate frame is oriented along the length of the element, and correspondingly the forces are also indicated with respect to dashes. And the other global coordinate frame, that is x and y coordinate frame, and corresponding displacements are represented by u and v. They do not have dashes on them. So the coordinate frame which has dash with it associated with it basically represents a local coordinate frame, and the other coordinate frame which is not associated with dashes happen to be a global coordinate frame. And in the xy frame, that is the global coordinate frame, what we are basically looking, what we basically want is a relationship between the displacement and force, which is going to be something of the type by the given by the equation on display. It basically is going to be a square relationship. The relationship which is going to be obtained between the two degrees of freedom and the forces, basically that is going to be a square matrix. And also notice that this particular matrix has displacement along the y-axis represented by V, and also forces along the y-axis represented by Fy. This is what the global relationship is going to be something like, where u1, v1, u2, v2 are the degrees of freedom of the two nodes in the global frame, and similarly f1x, f1y, f2x, and f2y are the corresponding forces acting at the two nodes. Accordingly, K is a square matrix of size 4 rows and 4 columns, which can also be written as F is equal to K into D. So this basically means that in a local frame, the relationship between forces and deformation, that is degrees of freedom, is a 2 by 2 matrix. But when we look at a similar relationship in the global domain, the relationship happens to be represented by a matrix of size 4 by 4. So obviously these two matrices are not going to be compatible. So the first step which we take in this process is to make the two stiffness matrix of equal size. That means we are somehow going to modify the local stiffness matrix, which is of size 2 by 2. We are going to modify its size from 2 to 4 by introducing some artificial terms in it. Thus, the deformation along the y-axis also needs to be artificially included in the local frame. And this can very well be done quite easily by an equation of the type on display. Please note that there are two additional terms which are now in picture, indicated by V1 dash, V2 dash, and corresponding forces along the y-axis represented by F1 dash, F dash 1y, and F dash 2y. And since there is no deformation along the v-axis and correspondingly no forces acting along the y-axis, uh, this is in the local frame. Therefore, we have introduced these two equations by placing plenty of zeros in the matrix, which is just going to be illustrated with respect to the highlighted area. So F1y basically is the equation corresponding to F1y and F2y in the local frame basically is related to V1y and V2y multiplied by plenty of 0. So this basically means that the two equations have been introduced artificially in this particular matrix, and correspondingly we are going to denote this particular matrix with respect to dashes. F dash is equal to K dash multiplied by D dash, which relates the local degree of freedom to local forces in the X dash and Y dash frame. Now this exercise does appear to be useless, but the advantage of carrying out this particular exercise is that the deformation and forces are now related through a square matrix of size 4 in the local frame also, and obviously in the also in the global frame. So now we have a matrix of size 4 by 4 between the local degree of freedom and local forces, and also between global degree of freedom and global forces. Now in the following slide, we will develop a between relationship between a vector relationship of a vector between the local and the global frame. In the next slide, we are going to develop a relationship to represent a vector in the global and a local coordinate system, for which we have a global system represented by xy, and there happens to be a vector which has been drawn in green color. The this is vector d, and obviously in this particular coordinate frame, the vector d is going to be represented as ui plus vj, where obviously I and j represents the unit vectors along the x and the y direction. And then comes your second coordinate frame, x dash y dash indicated in blue, and in this frame also the vector d, this frame obviously is inclined at an angle theta with respect to the global frame, and in this plane or in with respect to this frame also, the vector d is going to be represented by u I dash plus v I dash, and where I dash and j dash happen to be the unit vectors corresponding to the x dash y dash frame. And now the relationship of the vector d in the x dash y dash and xy frame can be expressed as this equation, which basically is a trigonometric equation, obviously involving plenty of causes and sine terms. What in fact is not going to be obvious over here is that this happens to be a orthogonal matrix. So this is a relationship of a single vector between a local and a global frame. And since we have two nodes, that is node corresponding to u1 vector and the node corresponding to the u2 vector, we are going to use the relationship for expressing two vectors in the local and the global frame. Where in the local frame, the nodal displacements are indicated by dashes, and in the global frame, you have the degrees of freedom or deformations indicated as u1 v1, u2 and v2. Now this equation relates the degree of freedom in the local to the global frame, or in matrix approach, d dash is equal to t multiplied by d. And also notice here, since d dash and d both happen to be a column vector, that is a column matrix, uh, they are represented by curly matrix, curly brackets, where the matrix in between uh, is, that is the transformation matrix, is represented by square brackets. Now this obviously is a relationship between vectors, and since force itself is a vector, we can use the similar transformation matrix to have a relationship between forces in the two frames. We can use the same transformation matrix as a relationship between forces acting at the nodes between the local and the global frame, which gives us a relationship f dash is equal to t multiplied by f. Now collecting all the relationship together, we have a displacement relationship given by equation number 1, which in fact is a known relationship between, because we know the angle of inclination between the uh, two coordinate systems. Similarly, the force matrix is also identical. This also is a known relationship. A force versus displacement in local coordinate given by equation number 3 is also known. But what is unknown is a relationship between forces and displacement in the global frame given by equation number 4, which happens to be unknown. Now equation number 4 is basically obtained by using equation number 1 and 2, which is going to be illustrated in the next slide. So we know equation number 1, equation number 2, equation 3, and equation 4 is not known. We simply are going to substitute equation number 1 and equation number 2 in equation 3 to give the equation on display, and on the left hand side there happens to be a transformation matrix. This we can carry it out on to the right hand side. So obviously it is going to be carried towards the right with an inverse sign, and since it has been pre-multiplied, it is going to be pre-multiplied on the right hand side also, but it is going to be with a inverse sign. And since the transformation matrix happens to be an orthogonal matrix, this basically means that the inverse can be replaced by a transpose of a matrix. For an orthogonal matrix, the inverse of a matrix is equal to its transpose. So we are basically replacing the inverse with respect to a transpose. Now what we get over here is a relationship between f and d, and there is going to be a transpose of a matrix multiplied by k dash, which is a local stiffness matrix, and then multiplied by t. And since this can be written as f is equal to k into d, which basically is a relationship between force and displacement in the global frame. where K obviously is going to be represented by T transpose multiplied by K dash into T. Thus, if we know the stiffness matrix of a bar in the local coordinate system, we can easily find the stiffness matrix in the global coordinate system. For this, the only additional information which is required is the angle between the two coordinate systems. Now, in this particular slide, we are going to simplify equation number 1. So we know the expression for K dash, which is written in equation number 2. We know the transformation matrix that is given in equation number 3. Substituting these equation number 2 and equation number 3 in equation number 1, we get the expression for the global stiffness matrix K, in which the terms such as C and S represents cos theta and sin theta, and obviously it can be noticed that the matrix K has certain properties such as K obviously is a square matrix of size 4. It happens to be a symmetrical matrix also. But what perhaps is not going to be evident over here is that K is going to be a orthogonal matrix also. And once the K matrix is known, we can uh, solve the problem given for the displacements of the displacements at each node. And once the displacements are known, we can find out the strains and the corresponding stress for each bar in a local frame. We are not supposed to find the stresses and the strains in a global frame, but we are supposed to find the stresses and the strains in a local frame. Now, this should be clear the why we are not finding the strains and the displacements in a global frame, but why we are finding the stresses and the strains in a local frame. This should be clear from your elementary strength of materials knowledge. So we now know the displacements in local frame. Obviously, the displacements V1 and V2 are going to be 0 because the bar basically is deforming along the positive x-axis. There is no deformation of the bar perpendicular to the x-axis. So, the terms V1 and V2 are not present over here. And similarly, there are going to be no forces perpendicular to the x-axis, that is perpendicular to the bar only. Once the nodal deformations are known, we can find the stresses in each bar from its local deformation in local frame. So we can use either the value of F1 or F2. So in this particular case, we are using the value of F2, and why we are not using the value of F1, this is left out for the reasoning of the students. They can argue among themselves that why we are using the value of F2 and why we are not using the value of F1. So F2 is given by expression on display, and once F2 is known, we can find the corresponding stress simply by dividing the area. Therefore, stress is given by E divided by L multiplied by a matrix containing -1 and 1 multiplied by the local degrees of freedom. Now, this particular relationship we can modify it slightly. This relationship can be extended to go to global frames, such as we introduce the relationship between the degree of freedom between the local and the global frame to give the equation on display, where transformation matrix T is now going to be, which can further be simplified. Now these equations, these relationships which have been displayed, which have been developed so far, are now going to be used to solve a particular assemblage. So for that, we take the same example which was on display earlier. There are three bars connected with respect to pin joints. Each bar has been taken as an independent element. So there are going to be three elements, element number 1, element number 2 and element number 3, and there are going to be correspondingly 4 nodes. Now each bar has its own local axis oriented along the oriented along its length, that is starting from 1. Since all the bars are arbitrarily oriented, we need to define a coordinate system local to each bar. So this means that there are going to be three coordinate frames, three local coordinate frame, specific one specific to the each element. Now the positive direction of each local element, each local coordinate frame is from element number 1 or node number 1 to the other node. The direction of positive x-axis in a local frame is from node number 1 to the other node of the same element, which basically means that when you talk about element number 3, the x-axis and the x-axis in the local and the global system, they basically are the along the same axis. But for element number 2, the two axes are inclined at 45 degrees, and for element number 1, the axes are perpendicular to each other. So for bar number 1, the angle of inclination happens to be 90 degrees. For bar number 2, it is 45. And for bar number 3, the angle of inclination between the local and the global domains happens to be 0 degree. In the next slide, we will find the sine and cos of these angles, which are going to be used in the respective stiffness matrix. So this is a stiffness matrix in general. This is the formula which is going to be used. And then for the three elements and the three angles of inclination, we have tabulated the value of the cos and the sines which are going to be used for finding the stiffness matrix of each element. So we start the solution from element number 1. This is the formula which is to be used. The value of theta is pi by 2. We know the value of length, we know the value of elasticity, area of cross section, which gives us the stiffness matrix for element number 1, but it is now in global frame. And also notice that the degrees of freedom for element number 1 have also been indicated. That is U1 V1, U2 V2. In fact, the degree of freedom uh, are going to be used to assemble the three stiffness matrix of the three elements into a common global stiffness matrix. Similarly, coming to element number 2, for element number 2, the angle of inclination happens to be 45. And similarly, for element number 3, angle of inclination is 0. This pi by 4 is a typing mistake. So once the stiffness matrix of all the elements have been obtained in a global coordinate system, we are simply going to substitute the stiffness matrix of each element into a global stiffness matrix. And since there happen to be 4 nodes and each node has 2 degrees of freedom in a global coordinate frame, there happens to be 8 degrees of freedom. Therefore, the global stiffness matrix is going to be of size 8 by 8. So we start with a 0 matrix of size 8 by 8. Also notice that the global degrees of freedom have also been written in the global stiffness matrix. Global degrees of freedom are U1 V1, U2 V2, U3 V3 and U4 V4. So these global degrees of freedom are going to represent a row also, and they are going to represent a column also. And then we are going to transfer the stiffness matrix for element number 1 to the global stiffness matrix. So this -1 from the local frame to the global frame comes at this location, and similarly 0 from the local to the global frame. So the stiffness matrix of element number 1 is indicated in black, so you can very well know the positions which are going to be utilized by the stiffness matrix of element number 1 in the global matrix. The rest of the terms which are zeros in the global stiffness matrix represents that we do not have contributions from any of the element at these positions. Element number 1, the position occupied by contributions of element number 1 are indicated by positions which are black in color. Similarly, coming to element number 2, now element number 2 is going to be transferred from the local stiffness matrix to the global stiffness matrix. But the thing is that the global stiffness matrix already has some contributions from element number 1. Therefore, there are going to be some cases, there are going to be some positions where the contributions of element number 1 and element number 2 both are going to overlap. So at these positions, the numbers are supposed to be, the contributions are supposed to be added together. And these are the positions indicated in yellow in color. So it can obviously be seen that the contributions of element number 1 and element number 2 are in first row first column, first row second column, second row first column, and second row second column. These are the columns corresponding to U1 and V1, that is the degrees of freedom corresponding to node number 1, and the contributions of both the elements are overlapping corresponding to degrees of freedom for node number 1, because node number 1 happens to be shared by both these elements. Both element number 1 and element number 2 are sharing node number 1. In fact, element number 3 also has a node number 1, which means that the element number 3 is going to contribute at these specific locations also. Element number 3 is also going to contribute some terms at positions which already has contributions from element number 1 and element number 2. So what we finally get is a matrix of size 8 by 8. This is the final matrix which we are going to get. This is the final global stiffness matrix indicated by capital K. And since this is a relationship between global degrees of freedom and global forces, so we have the corresponding degrees of freedom written uh, in matrix form. And if you just take the trouble of finding the inverse of matrix K, it should come out to be the determinant should come out to be 0, because this matrix simply represents a motion of a rigid frame, rigid body. Therefore, we should before solving this particular matrix, we are supposed to apply some boundary conditions into it before we can solve this equation. So the boundary conditions are obviously the known values of displacements. So we have the frame on display once again. The terms which are known happen to be terms corresponding to constrained nodes, since node number 2, node number 3 and node number 4 are constrained. Therefore, U2 V2, U3 V3 and U4 V4 are going to be, all of them are going to be 0. And obviously, there is some force applied at node number 1. So, since this particular force is acting along a negative y-axis, there is no force acting along the z along the x-axis. So, F1x is 0 and F2y happens to be minus 10,000 pounds. The unknowns are displacement at node number 1, that is U1 and U2 both are unknown, and obviously the reaction forces where all the nodes happen to be constrained, all the forces are supposed to be, they are also supposed to be found. They basically are the unknowns obviously. So the boundary conditions are supposed to be applied in the equations which we have obtained earlier. This equation, and it might appear that this is a relationship between 8 variables given by 8 simultaneous equations, and it might appear that this is going to be a tough job as far as the solution is obtaining a solution is meant. But the thing is that there are plenty of deformations where they are the displacement is 0. All the displacements corresponding to U2, V2, U3, V3, U4, V4, U4 and V4 are simply 0, which basically means that the third column, all the terms of the third column are being multiplied by 0. Similarly, the fourth column, fifth column, sixth column, seventh column, and the eighth column. All these columns are basically multiplied by 0. So what basically remains is terms which are present in the first column and the second column. Now we are further going to reduce this further. Okay, only the first and the second column have been retained. All the other columns have been neglected. And if now you look at these equations, uh, because forces acting on the second node, third node, and the fourth node are not known, it basically means that we cannot use the third, fourth, fifth, sixth, seventh, and the eighth equation. But when you talk about the first and the second equation, the forces are known, only U1 and V1 are not known. So basically, we are going to use these two equations to solve the value of U1 and U2, which means that we are not going to use the third, fourth, fifth, sixth, seventh, and eighth equation. Only the first and the second equation is going to be used for finding the value of U1 and V1. And this gives us two equations, two unknowns, which can be solved easily to get the value of U1 and U2. Obviously, when U1 and U2 have been found, this can be substituted in the previous equations. This can be substituted in this equation to find the value of F2, F3, and like that. So basically, we can find all the reaction forces. And obviously, once the displacements have been found, we can manipulate this further with respect to the equations developed earlier to find the values of stresses. So this is basically the general approach for this particular assembly. And now we are going to have a slight discussion with respect to the symmetry of structures. Symmetry is one of the concepts which arises frequently in every assemblage, and it is frequently possible to reduce the system, overall system, to a smaller system by taking symmetry into account. This obviously reduces the number of degrees of freedom to be dealt with. So this basically simplifies our work. But there is a caution also that it also introduces additional boundary conditions which were initially not present. And this is going to be illustrated with help of an example. So we are going to take an example of a fixed supported beam, and उसको बंद करो अभी Cinnavan. We are going to take example of a simply supported beam. It has a load twice L acting at the center, given by twice W, and node 1 and node 2 are obviously unknown, and at node number 2 we are supposed to find the deformation. So the deformation which is going to be present, which is going to be introduced, basically is also going to be a symmetrical deformation with respect to the center. And then we can divide the entire system. These are the two boundary conditions. The displacement and the slope also are 0 at node number 1 and at node number 3. So this happens to be the set of boundary condition which is already known to us. Then to take advantage of symmetry, we divide the system into two parts, which means this is the resulting load, resulting system. The length also reduces to half and the load also reduces to W from twice W. And what we now get is a system which is a cantilever, which is going to be solved for the slope and deflection to be 0 at node number 1, and this happens to be its deflection profile. But if you compare the deflection of a cantilever with the deflection of a simply supported beam, obviously the two displacements are not identical. So what this means is that the approach which you have taken is a wrong approach. What should have been done is that the displacement should have been identical to what is going to be present for a fixed supported beam, which is going to be obtained only if you introduce additional boundary condition at node number 2. At node number 2, basically the slope is going to be 0. So this is the boundary condition which is introduced additionally when you take the advantage of symmetry. Now we are going to illustrate this particular concept with the help of a second example also. The type of symmetry which may exist in a system happens to be reflective, mirror, skew, axial and cyclic symmetry. So we are taking a second example consisting of 4 bars. Bar number 1, in fact there is bar number 1, 2, 3, 4, 5, 6, 7, 8. 8 bars arranged in a particular manner. The length of all the bars happens to be same, and there happens to be a load twice P acting at node number 4, and node number 1 and node number 5 are constrained. So if you divide the entire system along in two parts, uh, that is a left part and the right part, what you get is a subsystem which is illustrated over here. Now please notice that since the entire structure is going to deform vertically in a symmetrical manner, it means that node number 2, node number 4 and node number 3 can deform vertically downwards, but they cannot have any axial deformation. This simply means that at these three nodes, that is node number 2, node number 4 and node number 3, node 2, 3 and 4, we are going to constrain the deformation along the x-axis. Because they are going to have deformation along the y-axis only, but they are going to have a deformation. They are going to have no deformation along the x-axis. So this is the additional degree of freedom which is going to be imposed. Uh, these are the additional boundary conditions which are going to be imposed at node number 2, 3 and 4. Now in the next lecture, we are going to take some solved examples. We are going to illustrate some solved examples of bar assemblage, and then we will compare all the solutions with respect to the solution obtained from FEM. We are going to actually solve them. We are going to get the exact solution also, and then we are going to compare the solutions which we are getting from the FEM analysis. Now that is the exercise which is going to be done in the next class. For the time being, this is where we are going to conclude the present lecture.